What Muriel knows very well to do is to prepare nickel 0 in situ, which is very difficult because nickel 0, as you may know, is very, very unstable. And organonickels are very difficult to handle because in general you need a hand glove, glove box and everything to do some very, very tedious and difficult chemistry. But in our case, with this very simple condition, complex of nickel bromide by bipyridine and reduction by manganese 0 in DMF, you can generate highly reactive nickel 0 very easily in any organic chemistry lab. No need to be a specialist of that chemistry. And in this case, we can expect that the highly reactive nickel 0 will insert into the nickel iodide bond and generate this aryl nickel compound. Actually, it works very well. The cyclization takes place as expected, and we get the vinyl nickel intermediate. And even this vinyl nickel does the beta elimination. We did not expect this beta elimination to take place, but it did take place, and we obtained the cyclization elimination compound, as with lithium. The yield is not extraordinary, and the selectivity is terrible, but I will show you that nickel has much more interest than lithium for other reasons and other substrates, because it is, of course, much more tolerant of functionalities than lithium is. For instance, you remember that we needed the acetal group to get this cyclization working before. So now we try to do it with a simple methyl terminal group, and the nickel conditions gives in only 42% yield, but still it's better than nothing. The cyclization works, and we obtain the expected product as a E to Z mixture, plus, of course, when we try to purify it, isomerization product, because this aromatized compound is much more stable. But you see that now with nickel, we are able to cyclize whatever the terminal group on the alkyne position. For instance, we can also put a phenyl, and the same condition we obtain in 54% yield, the expected compound, unfortunately with not a very good control of the double bond. What else can we do? The good thing is that the good news, that was also a good surprise, is that in contrast to vinyl palladium species, which are not nucleophilic, vinyl nickels are nucleophilic species, and we can use it to trap in situ electrophiles such as benzaldehyde that we can insert at the very beginning of the reaction in Barbier type conditions. And in this case, by generating nickel 0, we do the aryl nickel, cyclization takes place, and the vinyl nickel intermediate reacts directly with the benzaldehyde to provide the expected aldol products. As you can see, in very good yield, 91%, and the full control of the double bond. So this methodology is a tandem methodology, looks much more attractive than the simple cyclization I showed you before. We can also do that in the presence of the acetal, of course, and in the presence of the benzaldehyde, the cyclization takes place. We trap the intermediate compound, and we obtain the expected alcohol. So you see that the condensation on the benzaldehyde is quicker than the beta elimination of nickel etoxide. So we can take advantage of that to get these very fragile functions all together, no problem at all. We obtain the compound with a full control of the double bond. Of course, if we do an acidic workup of this compound, we hydrolyze the aldehyde and get dehydration at this stage, and we obtain the fully conjugated compound as expected also. What else can we do? Well, we can trap this kind of intermediate with many different types of electrophiles, such as these ones, for instance. This work has been done by Lucie Ardou during her PhD, and Marie Clément was doing a short stay. She was coming from a school of engineers, so she did a short stay of three months in the lab. And these two girls have just shown that the vinyl nickel can be trapped by many different electrophiles, alkyl aldehyde, activated chloroesters, benzyl chloride. Even Michael type addition can be done with acrylates and metacrylates. The yields are not very good yet, but I think we can improve those. And of course, allylation with allyl acetate, for instance. So that's a quite large scope for this reaction. How does it work? Because, I forgot to tell you in this case. Maybe you noticed that in this case, we are using only 10% nickel and not one equivalent. So we turn to a catalytic version in nickel. How can we do that? How does it work? Why is nickel catalytic in this reaction? Well, what we think is that, as I told you, nickel 2 is reduced by manganese 0 in situ, Manganese 0 is oxidized into manganese 2, and the nickel 0 inserts into the carbon iodine bond, gives this intermediate, cyclize, and then react with the electrophile to provide that. So at this stage, we think that probably the manganese 2 is able to transmetallate the nickel alkoxide to provide the manganese alkoxide and release the nickel 2 in situ. And so the nickel 2 can now be recycled and reduced to nickel 0. So that's probably because there is a big difference into the affinity of the oxygen for nickel and manganese that this transmetallation takes place and nickel 2 is released in the medium, available for further catalysis. So what else can we do with this type of chemistry? Well, we can take advantage of the mildness of the nickel chemistry to do an intramolecular version. We can have the aldehyde on the molecule. You can see, for instance, here, the insertion of the nickel and cyclization gives this vinyl nickel. And now the vinyl nickel can condensate intramolecularly on the aldehyde to give this single isomer of cyclized product, 60% overall cyclization plus condensation, only one isomer. So that was, Ochen did a little bit the same kind of chemistry, but using the Takai reaction, using chromium and nickel. But chromium is not needed. Nickel does it very well also. Actually, you can also take advantage of this reaction to do cascade condensation by using the insertion of the nickel here, cyclization, and maybe now the vinyl nickel can condensate on this aldehyde to provide this type of very strained five-member intermediate. Actually, we did that very recently. The yield is miserable, 20%. But, and there's also isomerization product due to the migration of the double bond. But at least it proves that in the principle, this can be done despite the strain due to this 5-member ring on this position. So maybe if we do a 6-member ring is here, we can improve the yields and get interesting compounds. Interestingly, you can also have the aldehyde in another position in which it will be unable to react with the vinyl nickel here. You can see here that this vinyl nickel cannot condensate on the aldehyde. So if you have benzaldehyde in the medium, it will react quicker. And after hydrolysis, that has been done also very recently, we can obtain this compound with preservation of the fragile aldehyde function, which remains in the medium, available for further transformation. Actually, this cyclization can also be extended to indoles, starting from iodoanilines. Actually, you don't even need to protect the nitrogen. You can work directly with the aniline. This work has been done by Mathieu Rouen. He has a name that explains he cannot work anywhere else than in Rouen, of course. And in this case, this nickel chemistry works very well. We obtain the cyclization product, and we can trap also the electrophile as before with the benzofurane. Mathieu, during his master time, has done a few examples just to show that the cyclization trapping works very well also. Well, you remember chromium did not work with the two other metals, lithium and palladium. So it means that we have now 2 carbons between the oxygen and the triple bond. And indeed, this reaction still works. The cyclization, 6-exo-dig cyclization works. We obtain this vinyl nickel intermediate, and we can either hydrolyze the reaction and get the mixture of these 2 products due to the migration of the double bond during purification. But we can also trap the vinyl intermediate with benzaldehyde and obtain this kind of intermediate, and acidic hydrolysis give directly the corresponding condensation cyclization product.